Welcome. So my name is Jacob Moody, and we're here today to talk all about Unicode. So just a quick brief about me. I work on Ninefront. I work on all sorts of stuff in Ninefront. I consider myself kind of a growing Unicode nerd. I didn't know much about Unicode before starting work on Plan 9, but have been growing that muscle. And I port stuff sometimes. It's kind of the bulk of the need to know. So I want to start with some historical context. And, this isn't exactly my story to tell, but I think it provides some good context. This happened years before I was born. But Unicode v1 was released in 91. Sometime thereafter, Plan 9 starts to kind of add support for this brave new 16-bit character world. And the initial port, at least according to Rob Pike, used an encoding from ISO 10646. And again, according to Rob, this was not very well enjoyed by those working on the system at the labs. At some point, Ken and Rob were asked to kind of vet a file system safe UTF design by some folks involved in the X-Open standards organization. In response, Ken designs what would become UTF-8 in response. Rob works on implementing support throughout the system, and under a week later, they ship out a build of Plan 9, everything included, that has this kind of UTF-8 support. And supposedly this was used as a argument for standardizing this encoding. So, Plan 9, stopped being developed by Bell Labs and kind of got out into the community. And of course, Unicode continued to change over that time period, well after Plan 9 had kind of stopped being developed at Bell Labs. Perhaps the biggest change to Unicode, and probably the biggest change throughout all of its history, was Unicode extended to 21-bit characters and V2 onwards. They initially tried to fit everything into 16 bits. It's a bit ambitious, but they ended up giving up on that, and we now live in this 20-bit character world. I believe, from what I could gather, 9atom was the first to implement support for 21-bit code points. And, likewise, we have some library functions which work using kind of the existing properties of Unicode characters. And we'll get a little bit more into that in a second. 9atom also updated for at least V2, I think a little bit beyond that as well. Thereafter, Ninefront starts to work on expanding to 21 bits and getting support throughout all of our software. And I wanted to just mention here, this is ongoing work. We still find bits and pieces of code that doesn't kind of meet our standards for what we would expect. Just this past year, there was some work pushed to Ninefront on allowing Unicode and YAC identifiers. So that's something new. Just saying that this is an ongoing effort. So I want to kind of walk through, how I was using the system, how I kind of found the need for some work to be done with Unicode. As I mentioned, Plan 9's libc includes some kind of rune variants of typical C functions. One of which is, there's the classical kind of Unix ctype.h function. So your two upper, two lower, is upper, is lower. Plan 9 extended these, and we have kind of two upper rune and is lower rune and functions like that. I had found that in Ninefront, these functions were never updated for characters above the 16-bit area. So, that 16-bit area has kind of been referred to as the basic multilingual plane. So we were missing anything above that, any other plane besides that BMP. Interestingly enough, when I kind of was doing research for this, I'd found that 9atom did update these functions for at least V2 and I believe also V3. But that work kind of never ended up making its way into Ninefront. So, this is an opportunity. I said, we should go about and fixing this. I will mention the existing implementation before this work started. It was just a big static array of all code points. And we did just a binary search through that big array based on the code point value in question. So two upper rune would take that rune, do a binary search through the big array, and then find the complementing rune in order to, return. So, when we're visiting this stuff, I started to think, Unicode is a evolving standard. It changes every year. It seems like now, it's not always been the case, but seems to be more recently. We get new stuff every year. So it's a treadmill, right? If we're going to write functions that support this interface, then we're going to need to, keep up with the Unicode standard as it evolves and changes. So I started digging into it. Is there some way that we could do code generation based on the information that the Unicode standard provides? Thankfully, the Unicode standard does publish very nice kind of awkable .text files that contain all of the necessary data that you would need for implementing something like this. In fact, the lib Unicode, which is provided as part of the original Plan 9 distribution, was itself a cut down variant of this Unicode data.txt. I believe the column differences were changed a bit, and things were converted from uppercase to lowercase. The Unicode standard tends to be a little shouty, I found. So, now we have kind of a plan of attack. We have our Unicode data.txt files. We'll write some code, we'll read through the standard, and we'll generate these functions as output. And this should hopefully allow us to, more easily keep up to date as the Unicode standard continues to develop and flourish. When visiting code like this, it's also important to ask the question, can I leave this in a better state than I found it even after updating it? And so it was worth the conversation to decide, hey, can we do something better than this binary search? I mean, the binary search is probably fine, but the number of characters in Unicode is only going to grow over time. So, the impact is going to, the time spent searching is going to increase over time. So the thing about the Unicode kind of code point space is that it's grouped kind of by language, and sometimes things grouped by things other than language. But the point is that it's organized. You have, like characters generally with each other within, kind of that code point space. And for these functions specifically, the two upper and two lower and is upper is lower, not every language has a need for these functions. CGK has no notion of casing. You can't convert a hiragana ideograph to uppercase or lowercase. That's not something you can do. So this kind of creates this, naturally you have kind of parts of the code point space where you have information that you need, and you have large swaths of the code point space where you don't have any mappings. And this kind of creates it's just a property of this data, and we can use this property to design an efficient lookup table that is both, expedient and, moderately sized. And in order to help with this, for specifically these two upper and two lower variants, it becomes advantageous to store not the resulting rune from the operation, but to store the offset, either positive or negative, from that base rune. This not only allows you to store large swaths of zeros in the CGK table space, but also to ensure, like, for example, the ASCII, classic ASCII range, uppercase A and lowercase a are the same difference away from each other as uppercase B and lowercase b. So, this allows, kind of like values in that area as well. So as I was working on this, I was discussing with other people, and Ori had sent me a book called Unicode Demystified. Fantastic read if you're interested in the kind of every detail you could possibly want to know about Unicode. But that book presents this kind of this data structure they call compact arrays. Now, the lookup of it's really just page tables. You construct them a bit differently, but really it's kind of just a page table lookup. So you start with, I'll kind of walk through how we build this. We start with a, one-to-one mapping in an array. We have a code point can be 21 bits. So we create an array that has, 21 bits worth of indexable values. You split up this index into equally sized chunks. So, say split everything into 32 values and 32 values and 32 values and 32 values and so on. what we then do is take the end of one chunk and the beginning of the next, and we walk backwards through the first and forwards through the next, looking for similar values. And for every similar value, that allows us to kind of overlay the chunks on top of each other, with the most ideal case being two identical adjacent chunks in which they can be entirely collapsed onto each other. Now, when you do this, you're going to, your one-to-one index no longer works. You no longer have 21 bits of addressable characters in this. So you need kind of an additional array, a higher level index, which allows you to kind of point into the same chunk for different kind of, virtual chunks. So this was that's kind of the basis of it. This is what I ended up going with for implementing a lot of these lookup tables, not all of them, but a fairly large majority. And as it turns out, it becomes advantageous to not just do this once, but to do this twice. So you do this compacting step on your kind of initial data lookup. And then once you have your kind of two layers, and once you have your two layers, you can then perform another compacting step on your kind of index layer. So you end up with kind of three arrays. You use the top one to index the middle one to index the bottom one. So you kind of end up with using kind of three sets of bits from the input for addressing each of them. So in terms of implementation, we have code for reading these .text files, and we're generating these compact arrays. We do these two layers of compacting. I wish I had a more sophisticated way of telling you how I picked how many bits were assigned to each of these tables, but it was trivial enough to brute force these and find the smallest generated table. So that's what I did. So, for the two upper, two lower, two title, I found that using 10 bits for the layer 2 index, 7 bits for the layer 1 index, and 4 bits for the bottom kind of data chunk layer seemed to kind of do the trick. For the is tables, the is upper, is lower, we used one single table that was filled with bit vectors. One bit was assigned one specific category that Unicode had assigned to that character. So we're kind of able to smush that all together. So that data table is a little bit more dense. There's not large swaths of zeros in that one. And for that, we had kind of it was pretty similar, just kind of 1 bit difference. We used 11 bits for the layer 2 index and 6 bits for the layer 1 index, and that same 4 bits for that bottom level chunk offset. So this is kind of our initial results from doing this. So our 2 upper, 2 lower, 2 title, it was we had just a little bit over 10K for each, and our combined is rune table was a little shy of 25K. So all in all, if you're using all of these functions, you're paying just about 60K worth of program size for having a constant time lookup for kind of all of these types of transformations, which to me that seemed well worth the expense. So what can we do next? Well, we now have this tool. We can parse these Unicode standard database files. We can generate these efficient lookup tables. What's the next, natural next thing that we want to do? And to me, I really wanted to kind of tackle this normalization problem. We have these data tables now. This is a more complex operation that we're allowed to do. And I also looked for some freebies. What are some easy algorithms that we can implement now that we have these tables? Turns out like both Grapheme breaks and word breaks are fairly trivial algorithms given you have the correct data tables. So those kind of came for free. These were an additional kind of, we have the tools, let's get that implemented. So before we go into kind of how normalization is implemented, I want to make sure we're kind of on the same page as to what Unicode normalization is and why it's necessary. So Unicode, for both historical and design reasons, has 2 ways to represent some types of characters. So we see in this example here, we have our kind of our uppercase U with this diacritical marking here. And we also have, the same character, visually to the user, represented here, where the first variant is there is a specific code point assigned to just this specific combination of uppercase U with this specific diacritical marking. In the other case, this, 55, this is our ASCII uppercase U that we've all come to know and love. And then this is a conjoining code point. This code point says to attach this specific diacritical marking to the character that is, the base character before me. So, these are, the standard has both of these variants, and this creates a problem, right? As a user, without knowing some of this context, you're seeing the same character. You're trying to log into a website, you're trying to open a file, and you're typing what you see on the screen, but the computer is telling you, no, I don't have a file, I don't have a user with that specific string of bytes. That you've given me. So this creates issues where you have kind of difference between what the user is perceiving and what the computer is comparing. So for the purpose of providing a better semantic comparisons, we need some way of converting any sort of text consistently into one form or the other. For this purpose, the Unicode standard defines two forms, so technically four, but the other two, they're not very important. We define, for this purpose, we care about NFD and NFC, normalization form decomposed, normalization form composed. So in NFD, everything that can be decomposed, everything that has multiple, that can be broken out into multiple code points is. Whereas the NFC is the inverse. Anything that can be recomposed, anything that can be used, represented using a specific tailored code point is used. Now, when you normalize to NFC, not everything is guaranteed to be composed. There are certain characters that can only be rendered in decomposed form. It's a bit of a gotcha, but that's a bit besides the point. Now, the algorithm which turns input text into one form or the other, that's normalization. So that's kind of what we're talking about here. So, like I said, we need some data tables. Let's talk about the data tables that we need. For starters, we need to be able to map either the composed rune into its two decomposed counterparts, and need to do the inverse. We need to map the two decomposed runes into its pre-composed counterpart. Now, Unicode always defines decomposition to be 1 to 2 or 2 to 1. But however, you can have multiple layers of decomposition. So I believe for one part of the algorithm, I needed to kind of find out and write code that figures out how many chains of decomposition can you go through before you're done. I believe it was 5. One character can be decomposed 5 separate times. So just keep that in the back of your head. Now, in addition to these two kind of, rune mappings, we also need the combining character class. This is important because when you have decomposed Unicode, to the user, say instead of having just one combining character diacritic, we have 2 or 3. This is common in languages like Vietnamese. You need a consistent ordering of these decomposed characters in order to compare semantically across multiple variants of decomposed Unicode. The property of these code points which stipulates how these are sorted, that's the combining character class. So we need this table as well. And we're also going to be needing this quick check value. This is used to kind of solve an edge case that's present in some of the chunking that we'll do later. I'll talk more about that in just a second. Conceptually, though, quick check is a pre-computed value detailing if a character is allowed in a certain form. So, for example, this specific U with combining diacritic as one code point, quick check would say, nope, not allowed in decomposed form. Similarly, something like this combinational right here, it would say, nope, not allowed in NFC. That's so that's that quick check table is providing for us. So both the quick check table and the combining character class are fairly easy to implement. They look very similar to our existing tables. They are implemented just as compact arrays like everything else. And we pay about, roughly 10K for each, Not too bad. However, the decomposition and recomposition tables, these require a little bit more engineering, specifically because we're dealing with we have to deal with multiple sets of runes, potentially 42 bits. Realistically, you're rounding that up to 32-bit words. But, let's see what can we do to kind of reduce that space sent. It turns out that for both decomposition and recomposition, there's a heavy bias for valid code points to be in the basic multilingual plane, in that 16-bit code point space. So for decomposition specifically, we also have, our input's the same as our other compact arrays. We have one 21-bit rune as input. Our output is just the two runes. We're going 1 to 2. So if we know that our outputs are very likely to be in that 16-bit basic multilingual plane, we can just smush them together into one 32-bit integer for our value for our tables. And this ends up working quite well. It's tenable to use compact array for this. But what do we do for code points that are above that basic multilingual plane? There's not many of them. At the time that I'd done this implementation, there was 158 code points that resulted in results above the basic multilingual plane. So for this, I kind of carved out a little set of the Unicode private space. When processing this text, it would be impossible for a normalization, a decomposition, to produce anything in the private range that's not allowed. So we cut a little bit out of it here to stash our extra 150-bit code points. And what we do is when you're decomposing one of these candidates, which produce one of these larger code points, we produce instead an offset from this base 0xEEE, E for exception. Beginning, and that is then used to index just a flat array that has the answers. So we just kind of tack on an extra, hey, it's only 158 runes. We'll just tack that on at the end. And this allows us to kind of maintain this constant time lookup. We may be reaching into two different tables, but it's still, we get our result from the first table. We know exactly what our offset is into the second table. We don't have to do any searching. Now, recomposition is a little bit more involved. So we do have that same bias, the basic multilingual plane. And, in this case, we're taking two 16-bit characters in the ideal case and outputting one 21-bit character. And as you saw earlier when I talked about kind of what bit value ended up working well, surprisingly, the large kind of chunk of a lot of these compact arrays were the actual index tables themselves. And extending that index table to not be 21 bits, but to be 32 bits, it blew up the size quite considerably to the point that it was worth exploring other data structures that we could use to implement this. So, we still want near constant time lookup. So, let's try a hash table, let's field it out. So I came up with this kind of, this is our hash table struct we'd use. We have our kind of our U32 int key, so our two kind of basic multilingual plane code points smushed together. And we have one basic multilingual plane output, that's our value. And next we'll talk about that's for collisions. Now, a little bit of a trick here is we need to kind of serialize this out to one big block of memory. Remember, we're doing code generation here. We can't have pointers that point to different parts of memory. It can't look like, a simplistic implementation of a hash table. So it's not too bad, though. We take kind of our initial buckets, our initial set of NKVs, and just write them out as raw bytes, which we can do as two uint32. So one for the key, the next is, again, that value and next kind of being smushed together. As for the collisions, we simply store them as an amendum to the kind of back end of our initial buckets. And that's where the next value comes in. The next value points to the absolute offset from the beginning of the collision space, where to find the next element in the kind of the collision list. So that works out pretty well. We can keep everything in this one big block of memory. I did search around. I tried pretty hard to find a hashing algorithm that provided some decent enough results. What I ended up with, again, at the time for version 16 was 512 initial buckets, which gave us about 555 collisions. So we had 555 exceptions. So, on average case, you're probably looking at about 1 to 2 collisions per entry. It's not too bad. I mean, it's a little bit more work than our compact arrays, but not by much. We're still, for these basic multilingual plane code points, we're still doing this in constant time. However, what do we do for code points that are above the BMP? Well, there's really not many of them. Unicode it's a little bit funny in that there's more decompositions than recompositions. While the Unicode standard states that they don't have a preference for one form or the other, there is a soft bias towards decomposed variants. So you have singleton decompositions and decompositions that work one way but not the other. So for recompositions, the amount of code points you have that kind of break this basic multilingual plane are under 40. I believe there are 37 or 38 in V16. So for the time being, just we have that exception array. If we see an input that is greater than 21 or greater than 16 bits, we just search this list linearly. There's like 30 of them. It could be done more effectively, but I haven't seen a huge impact so far. So could be better, but for now, with the limited number of them, not a huge deal. So how'd we do? What's our table sizes? The decomposition table ends up being a little bit larger. We're just a little tiny bit over 20K. And our recomposition table ends up actually being quite small in comparison. Again, a little bit more work for the lookups. And, we do have that exception table. But in total, 30K for having, every decomposition and recomposition mapping in largely constant time, save for a couple of edge cases, is fairly nice. So now let's actually talk about, how do we implement, the theory? We have our data tables ready to start actually implementing normalization. So the standard is a bit deceptive. It kind of explains things in these very abstract terms. It says, for normalization, all you do is you decompose everything, you sort the conjoiners by their combining character class, and then you recompose everything. That last step, that recompose everything, that's the difference between NFD and NFC. So if you're normalizing to decomposed form, you just decompose everything and sort. And then you'd also do that if you're normalizing to the composed form, but then walk through and put everything back together again. This everything bit is the kicker. As I mentioned earlier, you can have multiple chains of decomposition. So implementing this abstractly, as they suggest, you're going to be doing multiple passes through the entire string. This won't do. We can't, you can't build a streaming interface like this. We don't have infinite RAM. We have to find a way around limiting the amount of memory used for processing a single portion of the string at a time. So what you really want is to be able to take some string, start reading it, and build a context, build a stack. And then when process that individually, and then when you're done with it, you want the freedom to flush that out. So we can work kind of with a fixed amount of memory at a time. So for chunking, this is kind of the chunking method that I came up with. The Unicode standard's a bit clammy about how you're supposed to actually go about doing this. I find it a bit frustrating. This is what I was able to piece together was through a bit of trial and error, a bit of understanding about how the code points actually decompose and recompose with each other. But there may be some theoretical inaccuracies. But as we'll see earlier, this is a tested implementation. So broadly, you have two types of context. You have your first case where you have your base rune and your conjoiner. So that's kind of like that earlier example that I gave with the diacritical markings, where you have your kind of ASCII U and maybe 3 or 4 or 1 diacritical markings. This context is fairly easy to extend to. You simply continue to pull stuff onto your stack until you hit the beginning of the next context, until you hit the next base rune. You can tell this based on that combining character class, as I said. Base runes all have a combining character class of 0. So this is a nice while loop. You keep pulling stuff onto your stack until we hit a combining character class of 0. Not too bad. However, there's a second type of context, which is where you have code points that are made up of multiple individual pieces, but all of those individual pieces themselves are base runes. So this happens in Korean Hangul. You have each of the Hangul characters are composed out of multiple individual pieces. Those individual pieces are not conjoiners. They're their own characters in their own right. And this is a lot harder. I couldn't find a good answer as to how do I know when I'm finished with one and started the other. And this was something that actually had to be changed between this code was initially written against the version 15 of the standard and then updated to version 16. In version 15, the only case of this was Korean Hangul. You could special case just Korean text and handle that entirely fine. Unicode version 16 added another language that also has these properties, so this had to be generalized. What seemed to work was to use that quick check value, as I mentioned earlier. So we just grow context until we hit a boundary, and we define this boundary as a quick check saying it belongs in the form with certainty. The quick check values have two potential values. You either have a no or a maybe. They don't give you a yes. A yes is the lack of no or maybe. So we walk until we know for certainty that what we're looking at belongs in this specific context, and then we take everything that we have so far. This is a bit greedy. It takes a little bit, the context grows a little bit larger than it might necessarily mean to, but this is the best way that I found to kind of generalize this problem. So with that said, we have, there's some more edge cases. Unicode does not specify a maximum number of conjoiners that you can have to a base rune. They say you can have as many as you want. Unfortunately, computers don't have infinite RAM. We need some limit. So a subset exists. Unicode does define this kind of variant called stream safe text, where they say, okay, look, you get 30 conjoiners. No actual natural language is going to ever use this many, but that's the limit that we're putting on it. I imagine the idea is you have 30 conjoiners plus one base rune plus one null terminator fits in a nice even 32 bytes. Now, what do you do then if you're processing text and you get, one base U with 200 combining diacritical markings? Well, you're permitted to insert a new rune into the output, this combining Grapheme joiner, Unicode .34f. And this acts as a intermediary base rune. And so we implement this as part of our normalization. And the reason why we need this is a little bit subtle. Remember earlier I mentioned decomposed conjoiners have to be sorted by their combining character class. Now, in order to sort the combining character classes, you need to have all of them in one array. You need to kind of be able to bring the first element all the way to the end if need be. And so if we allow that context to continue to grow infinitely, we run into problems. So the combining Grapheme joiner, by acting as an intermediary base, it allows us to sort the conjoiners in chunks. So we can sort the first 30 conjoiners and put them on the actual base rune, then take the next 30 conjoiners, sort them as for the combining Grapheme joiner. And that's kind of the reason why this is necessitated for kind of implementing this within bounded memory. So we now have our implementation. How are we going to expose this to other programs? What's our library interface? We came up with kind of one state struct and two kind of base functions. You have one for initialization, and in this initialization, it takes in an existing state struct. It takes in a flag that specifies either we're normalizing to NFC if compose is greater than 0, or we're normalizing to NFD if compose is equal to 0. Context is whatever user supplied pointer they would like, and that is then kind of preserved and sent over to getRune, which is a callback that the kind of normalization algorithm calls to in order to grab more input runes depending on what it needs for the context. So you do that, you give it the function pointer, it starts pulling runes in. How do you start pulling runes out? Well, we have this norm pull function, which again takes that same state struct, takes a destination for where you would like to store the output, takes the size of the output, and then we have this flush argument. This one's a little bit tricky and a little bit annoying. So remember, as I mentioned, you have to continue to grow context until you see the beginning of the next context. So if we just see a base rune and we're doing the streaming interface, we do not know if, hey, the next rune could be a conjoiner, the next rune could be another base rune. We don't know yet because we haven't seen it. So we need to kind of keep one context buffered in the state struct until we know for certainty either we're getting more text or there's nothing left. This flush argument is what allows the caller to pass that information to the algorithm. So if you have 10 bytes, you give it all to the normalization algorithm and you're like, I'm done, there's nothing more, bar's closed, go home, you pass flush, and that kind of gets that last bit of context out of the normalization implementation. So, we decided that, streaming is kind of the more complex of the two between fixed interfaces and the streaming interface. So we did implement, fixed sized input interfaces as well, but these are all implemented using the streaming interface. And so we just have, rune comp and rune decomp. These are just NFC, NFD. We provide both rune and UTF variants for convenience. And these work, more or less, it's the same algorithm, just a different interface for it. It is worth noting, though, that if you do not have enough space in your output, because, normalization can expand the amount of characters or contract it. So, if you do not have enough space in your output is truncated. The kind of ideal caller for these functions was, hey, I have some standard. Standard says I have 256 bytes to work with for this, or 256 characters. I need to normalize it, but I know the output is going to be limited to 256 6 bytes. So that's what you would use this for. So the Unicode standard is nice enough to publish tests for us. The tests are fairly extensive, a couple tens of thousands of test cases. Very nice that they do this. This implementation was written against these tests. It was considered done once we had passed all of the tests presented to us. And, being able to bring these tests in was super useful. It helped identify the issues when upgrading between version 15 and version 16. So that was a huge win. And in addition to kind of the standard published tests, we also have some tests of our own, which are more testing the interface. So testing that the combining Grapheme joiner is inserted correctly, checking that we're, breaking conjoiners up at the right offset and stuff like that. And there's a couple of edge cases with there. It ends up you actually have a conjoiner which itself can be decomposed. So you can wind up in weird scenarios with that. It's an interesting edge case. So, we have this now. How is this used so far? Well, initially we have support now in 9friends TCS. So TCS can now convert input text into both NFC and NFD. So you can perform normalization on both a pipe input and file input. Likewise, Street Lisp, a Lisp that's being developed by Sigrid, has also been vendoring this implementation of normalization for the languages support for normalization on all platforms. So everything, they kind of took this implementation and are using it everywhere. So remember, I if you can remember, I talked about this a ways back, but we do also get a little bit of some extras here. These were easy to implement. So the Grapheme break and word break, these dictate kind of where one logical character to the user, so whether it be one pre-composed character or one base rune and decomposed conjoiners, it defines the beginning of the next base rune. This is different to normalization. That part is also part of normalization. No, these functions don't use each other. It's its own thing. So this was easy enough. I believe the implementation is like 60 or 70 lines of code once you have the tables. So these were easy enough to add. Likewise, word break too, that finds breaks between sets of words and long streams of text. And for these, we had, again, 2 implementations, rune, grapheme break, rune word break, same with UTF, and they just return the pointer starting the beginning of the next context. So where to next? What's the next step in increasing Unicode compliance within the system. Well, now we can logically handle decomposed Unicode now. We have the tools necessary in order to do that. The issue that we have now is our graphical user interfaces. Things don't handle decomposed Unicode very well. Our font system cannot handle it. It has this assumption that one code point is one character. Our user interface programs, Acme, SAM, Rio, these also have the same assumption. One code point is one character. That needs to change, whether that be a new lib frame, whether that be modifications to the existing one. That's still kind of something that needs to be researched. Also, it's not like there's the question as to exactly how to handle these cases. This isn't an agreed upon science either. Different languages may prefer different things. For example, I have a decomposed code point. If I hit backspace on my keyboard, am I expecting it to delete one conjoiner, or am I expecting it to delete the entire character with the conjoiners? And different people may have different expectations. So, finding out what the correct answer is for us is going to be, might be something that we have to kind of deal with. And yeah, I believe that's the last slide. So thank you very much. I hope you enjoyed this talk.
Yeah, thank you too. It was a bit long though, so we will have to keep questions and answers a bit short. And I will start with one that came up on the internet. And the question is about regexp. There is some special things like words, right? So \w or \b or white space \s. Are you also planning for doing something in that space so that you can recognize the Unicode with regular expressions? I'm aware, for example, of there is a vertical tab character, which is white space, but not just a normal space.
That's been discussed. I don't believe none of the discussions yet have come out with something that people have kind of been excited about to implement so far. So that's still in discussion. I believe there's a desire for doing something regarding that, but exactly what form it takes is at this point not something that we know.
All right, thanks. Do we got any other questions? Then please queue up at the microphone. Anthony is coming.
This looks like an amazing amount of tedious work, so thank you. I don't know if you've seen it, but Eric Quanstrom did a bunch of stuff with grep for sort of the Unicode version of case folding that might be relevant for this.
Oh, interesting. I must have missed that when I poked through 9atom. Yeah, I'll have to take a look. Thank you.
It was significantly later than the original, the 21-bit thing.
Okay.
And there were several points where you were describing things like the 5 layers of decomposition where I just started laughing. And I'm curious if you have an example of something where you can do the decomposition in one direction and can't put it back together.
Yes. So there are singleton decompositions. So you can have one code point which decomposes to one other code point, which the Unicode consortium has abused for trying to hide their dirty laundry in the closet of legacy code points. Singleton recompositions are blanketly banned. You cannot recompose one code point back into one code point. So that's one class of can go one way but not back the other.
Are there any other major Unicode algorithms that we'll probably need to be implementing in the future?
For doing this kind of logic stuff, there's line breaks. We may or may not want that. Grapheme break and word break can be useful in terms of like implementing editors. Line break is much more of like a typesetting kind of property. So not that I was aware of initially. But for stuff like rendering stuff, there is that text shaping and stuff like that, whether technically maybe Unicode algorithm or not, that's kind of a whole other thing that is kind of a big to do so far. There's So yeah, there's other stuff we might need. But if there is other stuff people would like, send me an email. We can talk about it.
All right, that's it for questions. So yeah, thank you very, very much. And we will also make sure that you also get a nice, cute little 3D printed Blender to your house. Thank you.
Oh, fantastic. Thank you so much, everyone. See ya.